Okay, hello and welcome everyone. My name is Samantha Vanham. I'm the coordinator at the Alberta Prairie Conservation Forum, and I help with the Transboundary Grassland Partnership, or the TGP, as we call it. Now, the TGP was established with the purpose of achieving better grasslands conservation outcomes by communicating, connecting, and collaborating across the TGP geography, which includes northern Montana, southern Alberta, and southern Saskatchewan. We hold quarterly meetings with our core team to maintain communication, and we also hold an annual workshop with the location rotating between Alberta, Saskatchewan, and Montana. Over the past year, we've also started sending out quarterly newsletters and offering quarterly webinars, which also rotate between the three jurisdictions. Today's webinar is brought to you from our core team member in Montana, Marisa, and we will be recording the presentation so you can refer back to it afterwards. If you have any questions, you can write it in the chat at the end, and we'll answer as many as possible following the presentation. Our speakers today are Marisa Sather and Alex Kumar. Marisa, I'll give you a brief introduction. She is the Assistant State Coordinator for the U.S. Fish and Wildlife Service, Montana Partners for Fish and Wildlife, based in Glasgow, Montana. She works with a large collaboration of conservation partners in eastern Montana to deliver habitat restoration and enhancement for wildlife at a landscape scale, with an emphasis on grassland songbirds and working with private landowners. And we have Alex Kumar here as well. He's a research biologist with the U.S. Fish and Wildlife Service based in Fort Collins, Colorado. His work focuses on the sagebrush and grassland ecosystems with particular emphasis on bird population dynamics, landscape modeling, and monitoring. So thanks for joining us today, Marisa and Alex, and I will pass it over to you now.
Great, thanks, Sam. Can you hear me okay?
Yes, I can.
All right. Well, hi, everybody. Thanks so much for attending and your interest in this topic. I volunteered myself and Alex to share with you the work we've been doing using acoustic recording units to monitor bird population response to management in eastern Montana. So I'm just going to set up the reasons for this work and the background, what we've been doing on the ground in eastern Montana, and then I'll pass it off to Alex to walk you through a lot of the details of how we're doing it. Let me see if my slides work. Hey. Okay, so I think just glancing over this audience, I probably don't have to spend long on this slide. We all know that grassland songbirds are in serious trouble in North America. These are, I guess we call them the Little Four, the Fab Four, endemic northern prairie songbirds that have been experiencing some of the steepest declines of any birds in the world. Chestnut-collared longspur, thick-billed longspur, Baird's sparrow, and Sprague's pipit have all experienced precipitous declines since we started measuring populations in the 60s and 70s. Where we work in north central eastern Montana in the northern Great Plains is really the heart of the distribution for these four species. It's also representing one of the most intact grasslands and sagebrush landscapes left in North America. As you can see from the grassland roadmap, grass layer on the left there, that black polygon on the left and the red polygon on the right is the general area we work with our Montana Grassland Partnership collaboration. And the map on the right shows the overlaid breeding cores from Happet models showing the core breeding distributions for those four species I just mentioned. So you can really see how this landscape is extremely important for these four species. However, there's definitely trouble in paradise. The risk to this landscape of tillage for crop production is still a huge threat. A lot of it is still suitable or semi-suitable depending on markets and volatility to being tilled for crop production. This is just a tillage risk model from Olam and Robinson from 2019. But many of them look similar to that. It's an ongoing threat in the region. So one thing that our program really tries to do is to work with grass-based businesses, livestock production operations to promote native grass cover wherever possible. So one form that takes is when somebody's no longer interested in farming a particular parcel of land, we'll help them reseed it to native grassland vegetation. And our greater collaborative has been doing about 5,000 acres a year and increasing pace. That's about 2,000 hectares or more a year in this landscape. The demand is really steady or increasing. The markets right now are favorable to livestock, and crop prices and inputs continue getting tighter right now. So that's a really good climate right now to seed grass. We try to do wherever possible the most diverse native seed mixes we can. Typically it's a wheatgrass or needlegrass base, and often we're doing some sort of water and fence installation to facilitate livestock grazing on those places. And then we use our Fish and Wildlife Service private landowner agreements that will essentially protect those restorations for a 10 to 20 year period on paper, and in practice, typically longer than that. So this is my little brag slide for our partnership here in Eastern Montana. We've just been a delivery machine in the past 10 years. These are just the ones that we have used our landowner agreements for, but it's over 100 restoration projects totaling over 50,000 acres just this last 10 years, and particularly the last 5 years. So this is a great thing, but kind of from a biological perspective, so what? Does it actually matter for birds? So that was really the inspiration for this project. Our goal is to monitor but the biological outcomes of this work, this habitat restoration and enhancement work. Problem is, monitoring, as a lot of you know, is really tricky, and staff capacity is limited. We don't have time to get to all these places. We don't have time to spend days and days compiling and crunching data. So we came up with this idea in about 2016 of targeted local monitoring for grassland birds because of the importance of these songbird species. But at the beginning, it was a really, excuse me, field intensive effort. It took a lot of time and boots on the ground in the field. In 2020, we were successful in receiving some internal Fish and Wildlife Service funds to purchase 36 acoustic recording units, or ARUs. And after that, we completed 2 pilot seasons, just getting them out there, trying to get some acoustic data collected and see what we could potentially do with it. In 2022, we got some SA, stands for Science Applications, again, an internal Fish and Wildlife Service funding source to hire a bird monitoring coordinator through the Nature Conservancy. And she started in the winter of 22 and 23. And that's when things really began to pick up for this effort. And then we reached out for science support to Alex and asked him to help us figure out, is this going to work? Can we actually detect trends for these species in our restoration work? So I'll pass it over to Alex here.
Awesome. Thanks, Marisa. Hey, everyone. Yeah, so Marisa brought me on to help out with the project, initially to sort of answer the question with the point counts that she was currently doing. Was she collecting enough data to have enough power to actually detect meaningful trends? And you don't have to worry too much about all the numbers here. Just kind of look at the magnitude and we can see everything from 500 all the way up to 30,000. And what these numbers represent is the amount of individual locations that point counts would need to be conducted at in order to detect a trend. In this case, it was a 3% increase per year over a 5-year period. So that amounts to about a 13% population increase during that 5-year period. And so we can see really huge numbers. And if we compare that to the column on the right, that's the amount of sampling that was done in 2021 for fieldwork. So we can see we're orders of magnitude off between what we would like to get to have the power to detect the trends we're interested in and what we're actually able to achieve on the ground. Thanks. Marissa's doing the slides, so there might be a little bit of a delay. So yeah, the main takeaway here is we're not able to sample enough points in order for point counts to be an effective monitoring technique. And so that led us to try to answer the question, can we pivot instead to autonomous recording units? So that's the next slide, Marisa. To try to use that instead to monitor population trend instead of relying on point counts. And so what we really were interested in is measuring population change over time. So initially, when we were doing point counts, we were assuming that counts of singing males relate to overall population abundance. so that trends in these singing males would relate to trends in overall abundance. Now we have to potentially relax that assumption even further when we're using acoustic recorders. And instead, we're looking at the call frequency of these males and wondering if that would then relate to overall population abundance. So trends in call frequency could potentially index trends in population abundance. And so sort of the overall goal here is to evaluate the effectiveness of these autonomous recording units to monitor trend. And to answer that overall question, we had a few different sub-questions, and this sort of outlines where we're going to go for a lot of the talk here. So the first question, or sort of sub-question here, is, can we use AI to analyze acoustic recording data? And to answer that question, we used a program called BirdNet, and we'll talk more about that in a second. Then the second question is, can we use data collected from these acoustic units to optimize our sampling design? So things like, when should we be collecting data in terms of the time of day or the time of year? How long should we be recording for a given duration? And we're hoping to be able to actually use data to answer these questions. Then the third question here is, if we're able to come up with an optimal sampling design, can we actually use the ARU data to monitor trend? So in order to answer that question, we first needed to take all the ARU data and come up with metrics that summarize them, and then relate the best metric to songbird abundance. And then we were going to compare the sample size needed for ARU monitoring compared to what we were doing with point counts. And then there's some preliminary results that Marisa is going to share relative to the work in Montana. And then finally, we're going to conclude with some considerations if anyone else is interested in using ARUs to monitor birds. So a lot of the logistical and sort of more feasible or feasibility considerations. So things like cost, sample size, how to deal with data management and analysis. So first question, can we use AI to analyze ARU data? And so currently a lot of data is being collected with ARUs. And in a lot of cases, it's analyzed either entirely or a subset of data is analyzed by manually listening to the recordings and actually identifying species present there. And that's a very useful technique, but it's pretty time intensive. And if you're hiring people to do it, it can be considerably costly as well. And so we're trying to come up with a monitoring program that we can really scale up. And in order to do so, we wouldn't have the capacity to actually manually listen to all of these recordings. So we wanted to explore alternatives to analyze the data. And so we played around with a few different methods of using AI, but we settled in on a program called BirdNet, which is developed from researchers at Cornell University. And it's basically a program that uses machine learning that you can feed a bunch of audio recordings into, and it spits out output in terms of likelihood that a given species is vocalizing during given intervals. And so we ran a lot of data through BirdNet, and then Marisa manually verified a subset of data. So she sat there and did the hard work of listening to all the recordings and transcribing when a particular species was calling, and then we could compare that to the ARU output. And for the sake of time, I don't have slides going into exactly that process. We can go there if people are interested. Definitely talk about some of the details there. But the main takeaway is, yes, we can use AI to analyze ARU data. We were able to see that BirdNet did a pretty good job of predicting when species are calling and also when they're not calling. So did a pretty good job using our methods to analyze the data there. So now that we know we can actually analyze the data with AI, we're now using the ARU data to try to optimize sampling. So first thing to consider is the best time of year to sample. So before, when we were doing point counts, Marisa was using her biological knowledge of the system and sort of pinpointed the end of May to late July as sort of that peak breeding window when birds would be vocalizing the most. And that's where we targeted the point counts. But with our ARUs, we can actually verify that with data. And so we set a few units out early or maybe mid-spring and kept them all the way through mid-summer. And we can see sort of how the vocalizations change on a daily basis. So this is sort of the daily mean vocalization over time. And the boxes in red are the window that Marisa used her biological knowledge to determine. And we can see that it's doing a pretty good job of capturing a lot of the peak vocalization there. And we can potentially do some statistics and really optimize the sampling there. But as a general first pass, we can see that we're in the right ballpark. So that helped answer when we should be sampling in terms of the time of year. And we can do the same thing in terms of time of day. So same thing, initially Marisa was sampling from 5 a.m. to 10 a.m. for all species. And we can see that that's when the peak of the vocalizations happen. But because ARUs can be deployed for as long as you want them, we could actually assess that and did a subset of recording every hour to be sure that we're capturing the peak there. And we see that 5 to 10 a.m. window is working pretty good for our species here. This example is Sprague's pipit, but it works well for others as well. And finally, we were interested in how long to actually record for. So we could obviously set it out for the full duration from 5 a.m. to 10 a.m. every day. But we wanted to consider, could we potentially do subsets of that time? And the reason we considered that is, there's still some costs in terms of needing to switch out batteries, needing to have bigger SD cards and things like that if you're having long amounts of recording. And so we're wondering if we could potentially have shorter durations and still get enough data to run our analysis. And so we tested the full hour and then 30 minutes, 15 minutes, 10 and 5 per hour. And then we correlated those subsets of data with the full 60 minutes. And we found that 10 minutes was sort of that sweet spot where we would get correlations greater than 0.99 for all species. So we're getting virtually identical data, but we're able to cut the amount of sampling by 6-fold. So that leads to a 6-fold increase in savings associated with battery and audio storage. So we settled in on using that 10 minutes of every hour in terms of how long we wanted to actually set these ARUs out there. And so we were able to use our ARU data to optimize our sampling design. And now with that optimal sampling design, we're really trying to get into that question of, can we use ARU data to monitor trend? And so just as sort of a refresher in comparison between what we were doing originally, point counts, and then using these ARUs, obviously an advantage of point counts is you can count actual individuals, but usually they're a pretty short duration because someone needs to be out there doing it. So it's usually 3 to 5 minutes, sometimes longer, but in general, it's a pretty short duration. If we contrast that with ARUs, maybe the downside is you can't usually distinguish between individuals, but an advantage compared to point counts is you can set them out for much longer durations, pretty much as long as you want, and have batteries and memory cards for it. And so in order to be able to compare these two things, we really need to know truth. So we need to know what true abundance is to see which of these two methods gets us closer to true abundance. And we're able to estimate true abundance by performing repeat point counts at a subset of a number of sites. So this example here is for chestnut-collared longspur, and it's 4 different sites that were visited. And they were basically point counts were done 4 times within a 3-day window. We use 3 days as a sort of a conservative estimate of population closure. We're assuming there's no movement of individuals within those 3 days. And we have those repeat point counts. And you can see that there's quite a bit of variability in between point counts for the exact same site, or for this exact same location within a particular site. And it's that variability in these point counts that you can actually analyze using end mixture models to get at an estimate of abundance that takes into account imperfect detection. And so I'm not going to dwell too much on equations. I think this is the only slide with equations on it, so we won't spend too much time on it. But just as a high-level overview for how these end mixture models work, we can focus in on the first equation there, that Ni. I think the next slide has it highlighted. Yeah, so that's site-specific abundance. The I there is just for each site. And we assume that's distributed with a Poisson distribution with a mean lambda. And then next slide shows us Y there. That's actually our data. So that's our point counts. I, again, is site. And then J is how many times we repeated it. So we had 4 different repeats, so J would be 4 here. So that's our data. Given our abundance there of Ni, we assume that's distributed binomially with the number of trials being Ni, and then P is your success probability, and you can kind of think of that as a detection probability. So it's this 2-stage model, and we analyze that using some Bayesian modeling, and we're able to estimate abundance from that. So it's sort of a graphic comparing the 2 different ways to get at abundance or index of abundance using ARU data. So what we just talked about, we had repeat point counts, we did end mixture models, and we ended up with an estimate of true abundance. And then we were going to compare that with our ARU data. So we deploy out ARUs, they feed out, we feed them into BirdNet, and it feeds out this output. That's a example output that you would get from BirdNet. And then we summarize that output into various metrics. And then we wanted to compare those metrics with true abundance. And so this is a summary of some of these results. We used R² to compare the ARU metrics with true abundance. And so before we delve into the results of the table, we can see there's a lot of metrics we considered. The first four are the sum of confidence greater than a particular threshold. So what exactly does that mean? We can walk through an example with output from BirdNet. So the confidence score that's circled there in green, that's given for every 3-second interval of the recording. So how BirdNet works is you feed it in a recording and it'll break the recording into 3-second chunks. And then you can provide BirdNet with a list of your focal bird species. And for every one of your focal bird species, for each of those 3-second intervals, BirdNet comes up with a confidence score that that particular species was vocalizing during that particular 3-second interval. And that confidence score is a number between 0 and 1. It's not an absolute metric in terms of probability that a species was vocalizing, but it's a relative score. So higher confidence means it's more likely that that species was vocalizing. And that's the main output that we used to summarize to come up with our ARU metrics. So if we look back at the table, the first one there is the sum of all confidence scores greater than 0. So basically it's the sum of all confidence scores. And then we considered thresholds of confidence greater than 0.2 or confidence greater than 0.5 or confidence greater than 0.8. And then we used a few other metrics based on some machine learning metrics like precision and recall. And then your F1 statistic is another way to sort of consider both precision and recall. And we can talk about that more if folks have questions. But in general, we found that those methods that required more analytical capacity were less supported than just summarizations of the confidence scores. And so we were really hoping that one particular metric would do well for all species. And we came pretty close. If you see the numbers highlighted in red, those are pretty high correlations for our 3 species there, Sprague's pipit and the 2 longspurs. But it didn't do so well for Baird's sparrow. Instead, the sum of confidence greater than 0.8 did better for that particular species. So moving forward, we used the sum of confidence greater than 0 for those 3 species on the right, and then the sum of confidence greater than 0.8 for Baird's sparrow. And so sort of the interpretation there is it's these high confidence vocalizations for Baird's sparrow that are most predictive in predicting abundance. But for the other species, even these lower confidence vocalizations have some important information in terms of predicting abundance. So that's sort of how you can conceptualize the difference there. But the main takeaway is we use similar metrics for 3 species, then we use a separate metric for the 4th species to really maximize the relationship between the metric and abundance. And then we're able to actually plot out what these relationships look like. So we have the ARU metric on the x-axis and then actual estimated abundance on the y. And we're seeing pretty strong linear relationships. We were interested to see if there'd be some sort of saturation or threshold effect as abundances got super high, and we didn't see any evidence of that. So these are examples for Baird's sparrow and Sprague's pipit. And again, the lowest correlation that we had was Baird's sparrow at 0.49, but Sprague's pipit was up at 0.75, so pretty high correlation there. And then we have examples for our other 2 species. The 2 longspurs and also super high correlations there. So that was really exciting to see that these metrics are really strongly correlated with abundance across the range of abundances that we're seeing at these sample points. So now we've sort of talked about all the different, I'm calling them ingredients that we would use to basically try to answer our question, can we use ARU data to monitor trend? And so this is going to feed into a power analysis. But basically now at each point count, we have true abundance that we estimated from the N mixture model. We have an ARU metric that summarizes the ARU data for the 3 days that it was deployed. And we also have 4 separate point count estimates from that same period. so we can compare the ARU metric with the point counts using true abundance to see the sample size needed for those two techniques to really evaluate trend over different effect sizes. And so in order to do that, we did a bunch of simulations. And I'll go through a quick overview. I have a slide at the end if folks have more questions on the specifics that we can walk through, but in the interest of time, I'll just sort of run through an overview and then get into the results. So the first thing we did is wanted to simulate trends in true abundance. So we used our abundance data to fit it to a distribution and then simulated a bunch of actual abundance data for a bunch of points and then basically fit that data to a certain amount of trend. So whether it's a 3% increase or a 5% decrease per year, we're able to get abundance data that way. And then the next step is we substituted in the ARU metric associated with a particular abundance estimate or a point count estimate associated again with that abundance estimate in the data. And once we made those substitutions, we now have data sets of the ARU metric or point counts. And then we can run a power analysis and see how much power we need for a point count versus an ARU metric to detect a trend. And then repeated it a bunch of times. And like I said, if folks have questions about that, we can talk about it in the discussion. But moving on to the results here. What we're showing here is the number of sites needed to detect trends of various effect sizes with 80% power. So we have our species on that first column there, and then things like a 3%, a 5%, and a 10% increase, or a 3%, 5%, and 10% decrease. And so we're seeing some pretty high numbers for like a 3% and even for some species a 5% change. But that 10% change, we're feeling pretty confident that we can deploy enough ARUs at enough locations to reach those numbers of sites required to get these 10% changes in the course of those 5 years. So we're pretty excited with that finding. That seems like that's logistically feasible for us to achieve. But then the final thing we wanted to do is actually compare that with the number of sites needed for point counts. And so that's what this graph shows. We have number of locations needed for point counts in blue. And we can see that for all species, the sampling needed for point counts is substantially higher than ARUs. And we have specifics on the next slide in terms of what those actual numbers are. You can see for point counts, it ranges from 250 all the way up to 3,000, depending on the species, whereas with ARUs, we're in the 50 to 500 range. And what that amounts to is about a 2 to 6-fold decrease in the amount of samples or the amount of sites needed in order to detect a 10% annual increase with 80% power. So that was a pretty exciting finding and sort of cemented our desire to use ARUs for monitoring going forward. And then I just wanted to point out here, one cool thing about actually relating the ARU metric to abundance is then we can use that relationship to transform a trend in our ARU metric to a trend in actual abundance. And that makes it a lot easier to communicate results with different audiences, landowners, instead of telling them that this metric of vocal activity related to an acoustic recording unit changed from 20 to 30, like that doesn't have much meaning to a lot of people. So instead saying we were able to double the amount of birds or something like that is a lot easier to communicate results with. So that's a nice little finding that we had as well. Now I'm switching it back to Marisa for some preliminary results.
See if I can unmute and advance slides at the same time. Thanks, Alex. That was great. So yeah, I guess back to our story of the work on the ground. We really wanted to put these things together and show or test the effectiveness of our restoration and enhancement work. And so for this first full-fledged year of ARU monitoring in 2025, we chose to focus on these grassland restorations. So we came up with 45 restoration sites of various ages. So I mentioned we had over 100 done in the past 10 years in our geography. So we came up with 45 of those that we could sample last year. We got ARUs deployed on all of those and then used just a linear model with a space for time substitution. So we took advantage of the fact that those restorations had different ages. Some were 10 years old, fewer were 10 years old. We had some and then various ages within. And we were able to use that linear model to estimate the effect of restoration on these 4 grassland species. Oops. So Barred sparrow in this case was our well-behaved one. This is kind of what we had hoped and expected to see when we did that analysis. Barred sparrow abundance increased over time based on years since project implementation of a grassland restoration in this area. So we essentially doubled abundance of barred sparrow by year 5 of a restoration and 18 times the abundance by year 10. And the 2 lines on there, one of them is just a quadratic smoothed out model, and the other one is a generalized additive model, which allows for a little more bouncing around. So that's why they look different. The story wasn't always that straightforward for every species. Sprague's pipit had this pretty strong quadratic response. And again, we have lower sample sizes at some of these ages, but what we were really seeing there was a peak around 5 or 6 years post-restoration, and anybody who's been involved in a grassland restoration in arid systems might recognize that pattern. It's basically, it takes a couple of years for things to take off and really get to growing, and then as grazing and drought and things are introduced back, the height of that grass mostly decreases over time. So that might be what we're seeing there. And then kind of the opposite is what we saw in thick-billed longspur, where actually these guys like bare ground, they use crop fields in this landscape. So in some cases we're seeing a decrease, or on average, we're seeing a decrease in their abundance following seeding of grass. But what's a little bit encouraging about that is we are seeing that level off and maybe even pick back up after that first flush of growth starts to reseed. So variable but encouraging responses from our species. And chestnut-collared longspur was also a general increase, but not as dramatic as the barred sparrow. So implications of this, this is a AI-generated image of AI saving the prairie. So I guess maybe there is a little bit of truth and AI can help us save the prairie. Restoration can be highly effective in this landscape at increasing the site scale abundance of barred sparrow and chestnut-collared longspur and Sprague's pipit. Thick-billed longspur is a little more complicated. Restorations may impact them negatively, especially in the short term. But I don't see that result as a failure. I see it as an important thing to know as somebody who's helping put restorations on the ground. It's something we need to keep working on and be aware of. The results do not necessarily translate to other landscapes. I think that's important, especially maybe for this group. We have an intact grassland landscape. We have these species in the area. I don't think you could necessarily go to a crop field in Iowa, plant it back to native grassland species and see this kind of response. So it is context dependent, of course, as many things are. Yeah, this underlines that landscape context, weather patterns, and year effects are highly influential across the board. But one cool thing on that is that with enough ARU data and background data, we can actually start to pull some of those things out and correct for them, which is an exciting side note. But bottom line is this work shows that we can use ARUs and artificial intelligence to effectively help monitor biological outcomes of our projects, which is super cool. So I think back to Alex for this one.
Yeah, so we just wanted to conclude with some considerations in case you're interested in using ARUs to monitor local populations of birds.
Oops, sorry.
So sort of the main considerations here for our cost and sample size. Initially for this analysis, we used specific recorders called SM4s from Wildlife Acoustics, and they're rather expensive, about $1,000 per unit. So we were curious with comparing them with less expensive options. So we compared them with something called Audio Moss, and they retail for about 100 a unit, maybe 150 if you want to buy the waterproof case and batteries and things. And we found that there's a really strong correlation between output from those two different units, right? About 0.9, sometimes even higher. So we were excited by that finding, and we've started incorporating Audio Moss into our sampling. And moving forward, we're going to primarily be using Audio Moss for a lot of the monitoring going forward. So think about 100. If you're considering doing it, we definitely recommend audio moss. Again, it's about 150 for the unit plus waterproof case. And if you're interested in these particular species, we're saying your ideal sample size would be maybe around 500, as long as you're okay with the 10% trends annually. If you want more specific trends with like 3 or 5%, obviously you're going to need to increase your sample size. But if you're okay with that 10% level, 500 should suffice.
And Alex, can I jump in quick?
Yeah,
maybe that's where you're going. It's not 500
rotating
units.
Yeah, exactly. Yep. Yeah. So that was the next point, is that doesn't necessarily mean you need 500 units, because you can rotate them during the breeding season. So and again, we set them for 3 days before rotating it. So maybe think about that as a starting point. But we considered maybe rotating 4 times during your breeding season. You could potentially do even more than that, and potentially need to use even less audio moss. But if you rotated 4 times, you can think of about 125 units needed, plus some extras in case things break down. So maybe 150 units. And so what would that run you? About $22,500, plus maybe throw in some costs for batteries and SD cards. So about 25,000, maybe ballpark that. But that's just for one particular treatment, right? So if you wanted to simultaneously look at a control and a treatment group, you would need to double that to $50,000. And again, that's not including field labor. So that's sort of a rough estimate of costs and the sample size needed to think about. And then in terms of data management, again, you're going to need lots of SD cards, lots of storage, batteries. We use a lot of external hard drives, and then we wanted to back things up using the cloud and made sure stuff was publicly accessible. So it's not an insignificant amount of time to manage all this data and be sure that, depending on what your requirements are for collecting the data, be sure it's backed up and accessible for the people that need access to it. So something to definitely consider allocating time for. And in terms of analysis, BirdNet is super easy to use. You can actually code in things using R, but they also have a GUI, a graphic user interface, which is super easy to use. You just kind of use the drop-down menus there and point to where all your audio files are stored on your computer, and hit a couple of those drop-down menus and click a button for analysis. And then it's going to give you the output that we showed you earlier, but just as a reminder, we'll show it here again, where you have, for every 3 seconds, a confidence score for all the species you were interested in. So then it's really easy to input this into R and subset it based off of the species or a confidence score and summarize metrics that way. Yeah, and so feel free to ask any questions related to this topic. Marisa and I are always happy to help, even if it's related to analysis-wise or data management. We're happy to help. We also have a manuscript that we've submitted that we will share if it gets accepted. So hopefully we'll be sharing that. I think Marisa can send it out to the listserv, or maybe Samantha can once we finalize that. And yeah, I don't know if you have anything to add, Marisa, but otherwise we can take questions if there are any.
No, yeah, just thanks for listening, and happy to, I think we have a little bit of time. Love to have some questions from you guys.
Yeah, thank you so much, Alex and Marisa. That was awesome. Okay, we do have a question. Are you able, I think it's, let's see, Cliff, are you able to unmute yourself? Yeah, I can hear. Oh, there we go.
Now I got it. Double unmute. Okay, super. Thanks for that. That was very interesting. Just on a same topic, but broadening it out. So if you're monitoring for everything, bird-wise, in an area, what are the costs for processing go up? So, you know, if you've got a certain subset target, maybe that's a lot cheaper. Maybe it doesn't cost a lot more to add all the other species if you're just talking kind of presence, absence kind of stuff.
Maybe let you try that, Alex.
Sure. Yeah. So first I'll answer it for an abundance standpoint, and then we'll get back to the presence absence like you mentioned. If you're okay using a metric like the sum of confidence for all species, it won't really cost too much more. You're already sending out the ARUs out. You don't need to validate the data, and you can summarize it all and run the analysis. So it'd be really, really pretty easy to do. The caveat is if you're using species beyond the 5 that we analyzed and you want to select the best metric, then you'd want to conduct point counts for those particular species, estimate abundance for those particular species, relate it back to the various metrics that we tested, and then select the best metric there. So that's where it could be significantly more complicated to get at that inference. Dollar amount, that's a little hard for me to estimate. It's more just you need to be able to collect the point counts, run the analysis to estimate abundance. It's actually kind of a similar question for presence absence, because with the ARU data, again, you get that confidence score between 0 and 1. So if you're doing presence absence, you want to come up with a threshold above which a confidence score you'd sort of assume presence there. And so ideally, you'd want to validate that with field data. So you would need to potentially either listen to the recordings or have an occupancy analysis that you've done separately to compare it to figure out where you want that threshold to be. For these species, we kind of have that figured out, but for other species, you would potentially need to do that.
Right. Which I always come back to. There's always a human element involved in this. We can't just let the machines do it, which gives us fun in the field.
Exactly.
Thanks.
Yeah, one of the great advantages, I'll just add, Cliff, to using ARUs is, okay, so we're focusing on these 4 species for this example, but we have recording data that doesn't discriminate. So we could always go back and look at another species or ask another question with the recordings that we have.
Right. Yeah. Perfect. Thanks again.
Okay, so there was another question in the chat from Shannon. Where in the grasslands are you placing the recorders, and what are you using to mount the recorders?
I'll take a stab at that one. So we started out, this was another evolution. I started out with like heavy steel T-posts and then tall fiberglass. And then I realized they don't necessarily actually need to be that far off the ground. And in fact, sometimes that was encouraging things to perch on them or cows to rub on them. So where we ended up more recently is using just really about 18-inch rebar stakes. And you can buy them, they're like gardening stakes where the best ones have sort of a loop, or we've even put a hose clamp on them to hold up the weight of the ARU with a zip tie. And so we actually found, I can't remember if we tested it empirically or not, but we found that, I think we did a little mini side study to see if the height mattered for what it was capturing, and it really didn't. And in fact, the lower down ones on those 18-inch stakes were getting less wind interference too. So that's what we've been doing. Cows are still a challenge. Cows and elk, in fact, like to chew on microphones. So that's something we've tried various things about, but for the most part, it's been pretty good. I don't know if that answers the question, Shannon. Okay.
Okay, now I'm muted. Adam has a question, I think. Oh, I think you can unmute yourself, Adam. Or if you're not, it looks like you're unmuted, but I can't hear anything. So you could also try popping it in the chat if that's easier too.
Okay,
Yeah,
what
so
about now? What about
I can
now?
hear you.
Oh, yeah.
Okay, yeah, sorry, I was already off on my question. Okay, but thank you for letting me know. Okay, sorry about that, guys. First off, I have a stupid question. And basically basically you're saying that the frequency of bird call is correlated with abundance. And that's the overall takeaway, is like how often the birds are singing is correlated with abundance. And I just seems like kind of crazy to me that that's what was happening. And so I just kind of wanted to say it out loud and see if you guys had any response or similar sort of wow moments about that. And then I just kind of was wondering if you looked at any other types of ARUs besides those 2 that you mentioned. And also, I'm sorry, I was spaced out a little bit before, but in terms of validating the sounds, that you were hearing? Did you get any pushback from the reviewers about that, or do you have any thoughts about how to manage that process? Like how much interaction do you have in terms of listening and validating the sounds? Thanks.
Yeah, that's a lot of great questions there. I'll start off with just the reaction to the pretty strong correlation between call frequency and abundance, and then I'll pitch it to Marisa if she has her thoughts on it. Yeah, I mean, I was a little bit surprised because you'd think maybe there'd be some sort of density dependent interactions in terms of how frequently birds would sing. But I did look at the literature for the manuscript there, and it's worked pretty well with things like nesting nesting seabirds in colonies. So that density relationship has been established in a few different places. And it seems like there might be an increase in call density in singing in the pre-dawn chorus, and density might play a role there. And so I think by starting at 5, we might have been able to mitigate some of those issues. But yeah, overall, it was a really exciting finding. I don't know if you had anything to add, Marisa.
No, just that really is like correctly pointed out, is like that is the huge central assumption that I was hoping we could make, and what Alex tested with this work that he's just presented. So I think once this paper gets out, I wouldn't be surprised if it was widely cited just to support that that single assertion right there. So it is exciting.
Yeah, and I'm trying to think back to the other aspects of your question. I think you mentioned using validating the data by listening to it, and Marisa did that. So yeah, we used 2 hours of recording data, and that yielded between 100 and in some cases almost 1,000 instances of vocalizations for a particular species. So we felt pretty comfortable with that sample size, that we're getting a pretty good representative sample to be able to assess how well basically the AI is doing to identify the species. But by using the metrics and then correlating it with abundance, that was sort of an additional test of how well these species, the AI is doing at indexing abundance. So the fact that we saw high agreement between the validation with the AI metrics, and then the high correlation between using the ARU metric and abundance sort of strengthened our findings in our minds. And I think there's a third part to your question, but
yeah, sorry, it was all over the place.
Yeah.
The third question was like, did you try the I think it's called the S2 song meter, the micrometer?
Oh, right.
Other unit, or did you have any? Would you like to test that one too, since it's a little bit more price competitive with the Audio Moth?
Yeah, I can pitch that to Marisa.
We haven't, Adam. We've looked at it, we've talked about it, but we weren't sure. Like, we were pretty happy with the Audio Moth, so we didn't think it, like, throwing a third one in there would necessarily do us any favors. But I bet I'm sure it would be comparable.
Yeah, cool. Thanks guys so much.
And then I see Shannon had a follow up. Yeah, as far as like where we're locating them in the project sites, we are trying to stick to a 10-point transect in each site that is spaced 300 meters apart between each point. And so if it's a big enough plot, that's all in a straight line. Sometimes we have to curve them a little bit and bend them around, but we're trying to keep those points 300 meters apart.
And I'll just note, we've been consulting on other projects that would follow up on this, and we're trying to keep that 300-meter spacing consistent. But in some cases, we're looking at a grid or some other sort of arrangement just to maximize the amount of ARUs we can deploy in a particular site.
Yeah,
so
and I think it's going to go that way too in the future with additional sites, just because. But anyway, the reason for the 300 meters is we're trying not to double sample birds.
I'm sorry. I'll ask another question if there's no other questions. Okay. So in terms of the placement on the ground of the unit, you mentioned like wind, but did you ever see any like or any perching behavior, or was it a place for the birds to stand on at all, or anything like that, or did you feel like I mean, or did you think about just placing them just on the ground? Did you kind of have any other ideas for how to place the units?
Yeah, perching meadowlarks. So particularly like if you use a T-post or something more substantial, and then those SM4s are pretty big. I think we get a little more perching on those. We've had meadowlarks hang out on them and then you can't hear anything else. The little audio moss, and they're kind of flopping on the rebar too, so they're not super solid as a perch. I think there's still maybe a little perching, but they're not super attractive. I have lost stakes in the field and tried just tying one to grass stems, and then they usually get destroyed by cows when you do something like that. And they become very difficult to relocate if you just put them on the ground. And I also don't, yeah, it might be worth testing the audio quality of those different locations. But as far as like a compromise between logistical, carrying things to the field and quality, I think the thinner 18-inch rebar with the small audio moss is a really effective place we've sort of landed in for Montana.
Okay, if anybody has any other questions, you can quickly raise your hand. Oh, we did get one. Here we go. Okay. So from Jaren, if the study were to be duplicated or repeated, is there anything you would have changed in your methodology, either in data collection or analysis?
Good question. I mean, it's still evolving, right? Yeah, I think it's interesting. It's, you know, coming from graduate school where you do a project and here's the answer and here's the report. Like this is just an ongoing. We just want to keep making sure our work is doing what we think it's doing and making it better. So I do think we, in some ways, have a chance to make it better every year. So I'm not really sure how to answer that one. Always more sample size. I wish we knew what we knew now 5 years ago, so we would have had the data already. But anything come to mind there, Alex?
Yeah, maybe I definitely second the higher sample size, and we have data on lots of species besides the 4 that we were originally interested in. So perhaps running some more of these metrics on more species so that inference can be extended beyond these 4 might be helpful. And yeah, more sample size in terms of more sites that we have those 4 repeat counts on to really establish that relationship would always be beneficial. But in terms of the general methodology and stuff, I think overall we feel pretty confident in it. But it's more like always, more data is always better in this case. So, and the cool thing is we can potentially rerun this analysis as we collect more data too, and see if these relationships get stronger or start to break down. As Marisa mentioned, it's an iterative process, so we're excited to continue with it.
Yeah, and if we can help anybody, you know, cut the first 3 to 5 years off of their process, we're very happy to help do that. Big of an area. Doug, I don't know the answer to the how big of an area 1 unit captures. We were just using an assumption that 300 meters would be far enough, but I don't think, maybe that's in the literature. Alex, do you know?
Yeah, there's been some studies, not necessarily with audio moss, but with other recording units. And generally it's thought that they capture the same amount as a human ear. So it's a similar sort of radius as you do for a point count. And so that 300-meter buffer we thought would be adequate for point counts. So I think it would also suffice for ARUs as well.
And then the microphones, I believe they're omnidirectional, but I can confirm that. And yes, anybody, that's so great point, Doug. One of the huge advantages to ARUs that we did not emphasize earlier is that anybody can do this. You don't have to have training, very minimal training on how to deploy it and set it up. You don't have to know your birds. You don't have to be out there at 6 in the morning on a beautiful spring morning. You can go in the afternoon, you can go in the rain, as long as you set it up and it captures a few good mornings of data. It's a lot more flexible on top of being able to be more powerful. It opens it up to more people can help and more time of day can be used to deploy them. So there's a lot of advantages there.
Definitely, and I'll even add, if you're interested as a rancher in just the number of the number of species that are present in your ranch, it's really easy to deploy one ARU, run through the analysis, and just maybe do a threshold of 0.8 and say if you got a capture of a particular species with a confidence above 0.8, then you can call it present and you can come up with a species list for your particular ranch really easily.
I believe there's some commercial products for people like backyard birders, and if you're just interested in your species list, that will do that automatically. I can't remember the name of it, but you can look that up.
Okay, I don't see any more questions in the chat, and we've only got a couple minutes left. But yeah, I guess I want to say, oh, here we go. Adam has put.
Oh, look at you go, Adam.
There
Thank
we
you.
go.
Yeah, I was just like, you guys, I have the answer to that question. Here it is.
Did we win?
Was it close?
Yeah, you did. You actually, you were, Alex was more right.
As usual.
That's awesome. Okay, so I guess with that, if there's no other questions, I really want to give a huge thanks to Marisa for organizing and bringing in Alex to this conversation and co-presenting today. That was huge. Marisa has been a core team member with the TGP for quite a while now, I think. And so thank you so much. Thanks to both you and Alex for presenting today. That was a really interesting presentation. And then thank you everyone for attending. I did put a really short survey up at the top of the chat. If you want to click on it before you leave, you can fill out. It'll take you like 2 minutes to fill out. And it will just help us improve and give us some ideas for future topics to do webinars on. And yeah, if anyone is not on the email distribution list for the Transboundary Grasslands Partnership and you would like to be, you can reach out to me and I can get you on that list very easily. But thanks everyone and enjoy the rest of your days.
Thank you, Sam.
Thanks.
Everybody.